Hi, everybody. Welcome to this video on matrix operations. We've got a lot to cover in this video, so no dilly-dallying. Let's get started right away with a definition. So we're going to first define how we can add some matrices. So to begin with, we're going to say for m by n matrices, A and B. So I'm going to say A is our Aij here, and B is the matrix made up of the Bij's. We will define A plus B to equal the matrix consisting of the entries Aij plus Bij. So in other words, to add two matrices together, all we do is we add those like corresponding things. So I'm going to take whatever's in the 1, 1 spot of matrix A and whatever's in the 1, 1 spot of matrix B, add them together, and that's my new 1, 1 entry. You can take whatever in, the 2, 5 spot of each matrix, add it together. That's my new 2, 5 spot. So matrix addition is not a super tricky definition. It's what you would hope and expect it to be. We're also going to define scalar multiplication, which is also a very nice definition. So scalar multiplication is going to happen when you have like a number times a matrix. So for m by n matrix, A equal to, and again, the Aij, and K, an element of R, we're going to define Ka to mean the matrix whose entries are K times the Aijth entry of A. In other words, to find the scalar multiple of a matrix, all you do is you take each entry of the matrix and multiply it by that number. So if we have, 7 times a matrix, that means every single entry of the matrix is going to get multiplied by 7. Okay, so now let's do our definition for matrix multiplication, which is going to be a little bit messier. Okay, so here's our definition for multiplying two matrices together. First, we're going to have an m by n matrix. Capital A equal again to our Aij's. And n by p matrix B equal to the matrix whose entries are Bij, then we're going to define AB to be the m by p matrix with entries the sum from K equals 1 to N of Aik Bkj. There we go. So this is our definition for matrix multiplication. We'll do a few examples to kind of see what it looks like in place and in practice. So in practice, it's a very visual process, and it's not going to be too tricky once we kind of get into it. But this notation is also going to be important for foreshadowing proofs. So we want to make sure we kind of are comfortable with this notation. We know what it means. So, or at least what to look for in the notation. So what we're going to do is basically, when you have your two matrices to multiply, you're going to take a row of A and a column of B and multiply entries together. Again, we're going to do an example so we can kind of see this visualization and process. But notice that in these summations, this is the ijth entry of AB. So yeah, I guess I could say AB, the ijth entry of that is equal to the summation. So what we're doing is we're keeping the I constant. So we're keeping a row constant. And then in A, and in B, we're keeping the column constant. So we're going to go up and down a column. So we hold those two fixed. And what we're doing is we're summing over K. So we move over along the row and we move down along the column and match up the corresponding pieces. So because we have this movement from across row and down column, also notice, hit things over here, also notice that we have M by N and we have N by P. So we're going to be holding the row fixed and we're going to be holding the column fixed in those corresponding matrices. And then these two components have to match up so that the summation works. So if you want to see if you can multiply two matrices together, you've got to make sure you have this piece kind of matching up. So that's a little bit of a preview into this notation, some things to look for. I'm going to reiterate it all when we do an example, but let's start out with some easy examples. Let's do some matrix addition. Cool. For this example, all we're going to do is we're going to add these two matrices together. Now, when you're adding two matrices, the conditions you need to have is that the two matrices are the same size. So in this example, we have two 2x3 matrices, so we're going to be able to add them. I'm going to write out a step I don't typically write out just so you can see what's going on behind the scene. If you want to write it out because it helps you to make fewer mistakes, by all means, feel free to do so. You know, for me, I'm just going to expect to see an answer after this because there's not a lot of mystery to addition of matrices. So what I'm going to do is I'm going to take this entry, and add them together. So 5 plus 1. That's going to be my new 1, 1 entry over here. Then I'm going to go to that. My voice is disappearing. I apologize. Then I'm going to move over to the next entry here and this entry here. Same game, going to add them together. So 4 minus 2. And then here we have -3 plus a 6. And so on. So I'm just adding the corresponding components of the two matrices. So usually this is going to be pretty easy to kind of do mentally. So typically we won't need to write that step. But it's helpful to have in your notes so you know where the solution came from, right? So we're going to get 6 and then a 5, a 2 and then a 5, a 3, and then a 0. There we go. That's going to be our A plus B. So adding matrices, hopefully not too bad. Just make sure, check your matrices are the same size to begin with, and then just add corresponding components. Okay, let's do one of scalar multiplication because that's another one that's not too bad. And then we can zero in on multiplication of two matrices. But first, easy things, scalar multiplication. On to some scalar multiplication. In this case, we're going to keep the same matrix A from the last example. And now we're going to find -half of A. So we're taking a real number and we're multiplying it by a matrix. So you can do this with any real number and you can do this with any sized matrix. So really nothing, you know, super heavy that we have to worry about in order to perform this operation. Again, I'm going to write an extra step just so we can see what's happening behind the scenes. And again, I'm not going to typically expect this first step to be written, but if it helps you, feel free to write it. So what we're going to do to find a scalar multiple of a matrix is we're going to multiply each entry by that scalar value. So I'm going to take -1/2 and multiply it by 5. I'm going to take 2 and multiply it by that -1/2. I'm going to take the -1/2 times 4, -1/2 times 0, and so on, right? So -1/2 times -3, and -1/2 times 1. And then we just compute these. Now, generally speaking, especially if your fractions have some fun denominators like 7s or 3s even, you're going to want to keep things in fraction form so that we maintain, precision with our solutions and we don't have any rounding errors. So there's nothing wrong with improper fractions. Write your improper fractions. So -1/2 times 5 is -5/2. Half of 2 is 1, so we get -1 here. Half of 4 is 2, so we get -2. Anything times 0 is 0, and anything times 1 is itself. And then -1/2 of -3 is going to be a +3/2. And that's it. So that's how we're going to get when we do a scalar multiple of a matrix. So hopefully addition, scalar multiplication, nothing mysterious, nothing, unexpected. Matrix multiplication is where we really need to be focusing because that's where, the weirdness is going to happen. So let's broach that subject now, shall we? All right, you ready for some matrix multiplication? Because whether you are or not, that's what we're going to do. So we've been blessed with 2 problems this time, just to give us some extra practice with matrix multiplication. So I'm going to try and indicate my visual process as I go through this. And again, I'm going to write down sort of a middle step that once you become fluent in matrix multiplication, you don't need to write. But especially when we're first starting out, it's super helpful to write it out to help show what your work is so that if you're making a mistake in your process, it's easier to catch. And when you're studying, if you forget how to multiply matrices, this is, again, some breadcrumbs so that you know, okay, this is what I did to get that answer. So for these first 2, we're going to multiply kind of following this first row and this first column. So because we're doing row 1 and column 1, this is going to be the 1-1 entry of our product. The way that we're going to do this is we're going to take the first entry in each of those and multiply them. So we're going to do 2 times -1. And then we're going to move over and we're going to move down. And we're going to do 4 times 4. And then we add those 2 things together. So we have our first entries get multiplied, our second entries get multiplied, and we add them together. Then let's find this spot up here. So this is now in the first row. So I'm going to look again at the first row, but now it's in the second column of my product. So I'm going to look in my second column here. So to get this 1-2 entry, I'm looking at row 1 and column 2. Now I follow that same process. So we're going to do 2 times 2 and 4 times -3 and add those together. Next, to get my first entry in my second row, now I'm in the second row. So I'm going to look at the second row of the first matrix. And I'm in the first column. So I'm going to look at the first column of the second matrix. And again, I'm going to kind of match things up as I go across and down. So my first entry here is going to get multiplied by my first entry up here. So 3 times -1. And then we have 1 times 4. So that's going to give us our 2-1 entry here. And lastly, we need the ballerina coordinate. We need our 2-2 position. So we're going to take the second row and now the second column to get that 2-2 value. So we're going to do 3 times 2. I move over and I move down. 1 times -3. And I add those pieces together. Now, one of the additional benefits of writing this out and making sure that we have a consistent system when writing it out is it does kind of provide a little check. So notice that my column entries here of -1 and 4 are showing up, the -1 and the 4 in this first column in the parentheses. And then here, my 2 and -3 are showing up here, 2 and -3. Moreover, my row entries here, the 2 and the 4, are showing up in front in the first row. And this 3, 1 is showing up here in this second row. So if you are careful and you write everything consistently, meaning like in the same order each time, you're going to end up with this sort of pattern evolving. Once we have all that, now we can just do those operations. So this is going to give me 16 minus 2, which is 14. This is going to give me 4 minus 3, which is a 1. This is going to give me 4 and -12, which is a -8. And then we have 6 minus 3, which is 3. So that's going to be the product of these two matrices. Now, I've provided a second example here for you to try out on your own. Walk yourself through it, see how you do. I'm going to walk through it as well, and we can compare answers. Okay, let's see how we did. So my final answer for part B was 4, -2, -1, and 13. So what I did, I followed that same movement. So I multiplied across the first row and down the first column to get this entry here. And then I went across the first row and down the second column to get this entry here. And then same kind of game, second row, first column for this one, second row, second column for this one here. Now, one of the other reasons, in addition to some like extra practice with multiplying matrices, one of the other reasons I wanted to do this example is because it reveals something, about matrix multiplication. So if I look at the two matrices that I multiplied, notice that in part A, the first matrix was 2, 4, 3, 1. And in part B, that was our second matrix, 2, 4, 3, 1. So we could think of that as matrix A. Then in this first one, we had -1, 2, 4, -3. And that was our first matrix here, -1, 2, 4, and -3. So we can call that matrix B. In part A, we found A times B. And in part B, we found B times A. And we are super accustomed in our world, in our lives, for multiplication to be commutative. You can change the order whenever you multiply, like 5 times 3 is 3 times 5, no problem. But with matrices, there is a problem because A times B gave me this matrix and B times A gave me this matrix. And they are very much not equal. So what that means is when we are doing our matrix multiplication, we can't be sloppy. We have to be very precise with the order of our matrices. And not only is this going to haunt us, when we're doing matrix multiplication, but also in the future when we go to solve an equation. We're so used to having things like, if I have 5x equals 15, we're used to just dividing both sides by 5 to get x is 3. But if we're dealing with matrices now, 5x equaling 15 is going to be different than if I had x times 5 is 15, right? I'm using numbers here for this example, but pretend those numbers are matrices. We're accustomed to these two equations being equivalent, and they won't be now that we have matrices. Because multiplication is not commutative, if we're going to define something like division, which we're kind of going to do, but not really, but if we're going to define division, we'd have to divide division from the left and division from the right, because those are going to give us different results. So not only is matrix multiplication kind of a pain to do, but it's also kind of a pain to undo, and it's gonna have these repercussions. You never realize how wonderful commutativity is until you don't have it. Now, we also did just a 2 by 2 times a 2 by 2. We did a nice kind of, these are easy examples of matrix multiplication. Let's kind of jumble everything up now and look at a few matrices and try and perform a variety of operations on them and see which ones we can perform, which ones we can't, and what our solutions end up being. All right, folks, we're going to work on example 24 now. And for this example, we're going to be trying a variety of products, seeing what we can do. And just to give myself some space to perform these operations, I've listed the matrices we're going to be multiplying or attempting to multiply over here. So we have M, N, and P. What makes this one a little bit different from before is notice that these matrices are not all the same size. And in fact, when you multiply matrices, they don't have to be the same size. They just have to have a particular size relationship. So in our definition, we mentioned that our first matrix was M by N. Our second was N by P. And when we find the product, we end up with an M by P matrix. So if you want to see, can I multiply two matrices together? First, figure out their dimensions, and then check the middle. If these two are the same, then you can multiply them, and you can think of it as like those kind of go away in the end. And our answer is this M by P. If they don't kind of do this little canceling thing, then you can't multiply the matrices. The product can't be found. It's kind of like if you try to divide by 0 with whole numbers, can't do it. Division by 0 is not defined. So matrix multiplication for matrices that aren't compatible dimensions is not defined. So for our first product here, we're asked to find N by M. So N is a 3, so we have 3 rows by 2. So we're going to multiply 3 by 2. And M is a 2 by 2 matrix. So we have to check. Are these two the same? Indeed they are. So we can multiply these two matrices. So I'm going to write out N first. 2, 5, negative 3, 1, 6, 2. And then we'll write out M, which is 1, 0, 3, and 4. Now, you might be wondering, like, they're not the same. How is this like system going to match up? Well, remember that because those two middle pieces are the same, the components that need to match up. So we have 2 things in this first row, and we have 2 things in this first column. So as we go through rows and columns, we're going to have the same number of entries in each one. Now, if I want to kind of set up what my solution is going to look like, this is going to give me a 3 by 2 matrix in the end. So if it helps you out to kind of write that out, give yourself some space. That might help you figure out where we're going to put the components. Now, when I perform these operations, I'm just really limited by board space. So I'm going to skip that middle step of just writing out all of that work. And I'm going to try and do the arithmetic mentally. So you all will have to check me because we all know how great mental arithmetic works. All the time, always perfect, right? So we're going to get here 2 times 1. So we've got 2 plus 0. That's a 2. Now I have 6 and 4 should give me a 10. So that's my first row. So now I'm going to move on to the second row. So 5 plus 0 is 5. And then 15 and 24. So that looks like 39. We're going to do our last row and our 2 columns. So negative 3 and 0 is negative 3. And then we have negative 9 plus 8 is a negative 1. So let's see how we did. Does that match my key that I made earlier? Also with mental arithmetic? Well, if I was wrong then, I'm wrong now. If I was right then, I'm right now. So I matched what I got. So we can still follow the same process and use the dimensions to guide you, so you kind of have like answer blanks to fill in. Let's do part D together, because that looks like it's going to be no problem, because it's NP, no problem. Hey. And then I'll give you a chance to try B and C on your own, and then we'll regroup and see if we get the same things. So for part D, N is again a 3x2, and P is a 2x3. Our middle components match up, which means we can find this product. And our answer is going to be big. It's going to be a 3x3 matrix. So let me write them out. So 2, 5, -3 is my first column. And then we have 1, 6, and 2. Next, we're going to get 4, -1, 1. And then 2, 3, and 0. And we're going to get a big old matrix in the end, 3x3. All right, so let's find this product now, shall we? So we're going to follow the same process as before, going across the rows and down each column. So we're going to get 2 times 4 is 8, plus 2 is 10. -2 plus 3 is 1. 2 and 0 is 2. So basically what I've done is I've done row 1 times each of these columns to get me these 3 values. So I'm going to help mark my progress here, since these are larger, I'm going to just cross that one out. And now I'm going to move on to the second row and do the same thing. So the second row times each of these columns. So this is going to give me 20 plus 12, which is a 32. -5 and 18, which is 13. And then 5 and 0 is just a 5. Okay, we're done with row 2 here. So we're going to do the third row times, again, each of these columns. So we have a -12 plus 4, which is a -8. A 3 plus 6, which is 9. And then a -3 plus 0, which is a -3. All right, and that's it. This is the product of N and P. All right, so take a moment and try finding the product of Mn and Pn on your own. And then, so pause the video, work through that, and then unpause and check against my work and see how we do. All right, so let's see how we did, right? So when I tried to find the product Mn, I ran into some trouble because M is a 2x2 and N is a 3x2, and their middle dimensions do not match up. So that means we can't find it. Mn is not findable. So then I moved on to part C, and I got a 2x3 times a 3x2. Those are compatible, and they're going to give me a smaller matrix, which is a 2x2. So we have this matrix here times this one here, and this was the result that I got. Now, one of the things that's odd, or started to feel odd as I was doing this problem, was I got a row of zeros to begin with. And we ended up getting non-zero numbers here. But one thing I want to point out that's strange about matrix multiplication is if I can get a row of zeros, there's probably some combination that's going to allow me to have zeros everywhere. And in fact, you can have two matrices multiply together and get a zero matrix with neither of those matrices being zero. So matrix multiplication is just, it's so different from what we're accustomed to, right? So you can't assume anything. You can't assume that it's going to be associative or commutative or have this multiplication by zero property. We can't assume we're going to be able to do division. It's just a mess. So we're going to do a few examples of applying these operations in the next couple of videos. And then we're going to delve into those properties to see which properties do these operations have. Addition is probably going to be commutative because all I'm doing is just adding individual entries, but we've already seen multiplication's not going to be. So will multiplication be associative? Can I change the grouping? Or is that going to break too? So we're going to find all that out later. For now, I'm going to say this video is done, and I'll see you in the next one. Till then, happy mathing.